Welcome, everyone. Today, we'll dive into an essential topic in machine learning, hyperparameter tuning. As many of you know, building a machine learning model isn't just about choosing the right algorithm. The way we configure and optimize that algorithm plays a massive role in how well it performs. So, what are hyperparameters? These are the settings we define before the training process even begins. They're different from model parameters, like weights and biases, which are learned during training. Think of hyperparameters as the knobs and dials we can adjust to influence how our model learns. For example, in a neural network, hyperparameters might include the learning rate, the number of hidden layers, or the size of the training batch. In simpler models like random forests, they could include the number of trees or the maximum depth of each tree. Why does this matter? Well, tuning these hyperparameters can be the difference between a model that predicts accurately and one that fails. Poorly chosen hyperparameters might cause your model to underfit, where it doesn't capture the underlying patterns, or overfit, where it performs well on training data but poorly on new data. Now, let's break down some key concepts to better understand hyperparameters and their impact. First, let's distinguish between hyperparameters and model parameters. Model parameters are what the algorithm learns during training, like the weights in a linear regression model. Hyperparameters, on the other hand, are defined by us. For example, we decide how fast the model learns through the learning rate or how long we train by setting the number of epochs. Here are a few common hyperparameters you might encounter. Learning rate. This controls how much the model adjusts its parameters with each training step. A rate that's too high might overshoot optimal solutions, while a low rate can slow down training. Batch size. This is the number of data samples processed before updating the model. A smaller batch size can lead to more precise updates, but might take longer to train. Number of layers or neurons. In a neural network, these define the complexity of the model. More layers can capture more complex patterns but may risk overfitting if the model is too large. To visualize the impact, imagine adjusting the knobs on a radio. If you tune them well, the sound is clear and crisp. But if you overdo it, the sound might become distorted or completely disappear. Similarly, hyperparameter tuning is about finding the sweet spot for each setting to ensure the model performs optimally. That's why it's so important to understand these settings, not just their definitions, but how they interact with the model and the data. Now that we understand what hyperparameters are and their importance, let's move on to how we can optimize them to get the best performance from our models. Hyperparameter tuning is essentially a search process where we experiment with different configurations to identify the combination that produces the highest accuracy or lowest error. Several methods can help us achieve this. The simplest method is manual tuning. This involves adjusting hyperparameters based on intuition or trial and error. For example, you might start by setting a learning rate of 0.01, test the results, and then adjust it to 0.001 if the initial performance is poor. While manual tuning is straightforward, it's often impractical for large-scale problems because it's time-consuming and relies heavily on experience. It's also not systematic, which means you might miss better combinations. To overcome the limitations of manual tuning, we have automated methods like grid search. In grid search, we define a set of possible values for each hyperparameter and systematically evaluate every possible combination. For example, if you're tuning a decision tree, you could test depths of 5, 10, and 15, along with minimum sample splits of 2, 4, and 6. This creates a grid of all possible combinations, which the system tests one by one. The advantage is that grid search ensures you cover the entire parameter space. However, it's computationally expensive, especially when the grid becomes large. A more efficient alternative to grid search is random search. Instead of testing every possible combination, it randomly selects configurations within the parameter space. Surprisingly, research has shown that random search often performs just as well as grid search, but it's faster because it skips many redundant evaluations. This makes it an excellent choice for large models or datasets. For even more complex scenarios, advanced methods like Bayesian optimization, genetic algorithms, or hyperband can be used. These approaches use more sophisticated strategies to explore the parameter space intelligently, often finding optimal solutions faster. While these methods can be very effective, they require additional setup and computational resources, making them suitable for specific cases. Now, let's talk about tips for effective hyperparameter tuning. First, start by coarse tuning. Instead of testing very fine-grained values, begin with a wide range and gradually narrow it down as you identify promising areas. This saves time and gives you a general sense of the optimal region. Second, always use a validation set to evaluate your models during tuning. Without it, you risk overfitting to the training data, which defeats the purpose of finding optimal hyperparameters. Cross-validation is even better because it averages performance across multiple subsets of your data, providing a more robust evaluation. Finally, automation is your friend. Tools like Scikit-learn's Grid Search CV and Randomized Search CV, or frameworks like Optuna and RayTune, can make the tuning process more efficient. These tools handle much of the repetitive work for you, allowing you to focus on interpreting the results. In summary, hyperparameter tuning is an iterative process that requires a balance of strategy, efficiency, and evaluation. Whether you're using basic methods like manual or random search or leveraging advanced algorithms, the goal is always the same: to configure your model in a way that maximizes its performance on unseen data. With these methods and tips, you'll be well equipped to tackle any tuning challenge. Let's take a moment to think about how these ideas can apply to your own projects.